And so now what we want to find is the mixture temperature, and we'll use a first law analysis. So very often when we have this adiabatic mixing problem, we're going to have the energy of this has to be equal. So the input energy equals to the output energy. And so we have the enthalpy coming in for each stream, and then the enthalpy of the mixture leaving. So if I write the first law, we have the Q dot plus M dot A HA plus M dot helium H helium is going to be equal to W dot plus M dot of the mix times H of the mix. And so, and I know that H is equal to C sub P, see? So I can find C sub P for the air and C sub P for the helium. I need to find C sub P of the mix. So H of the mix, so C sub P of the mix is equal to the sum of the Xi C sub Pi. So this is 0.955 times 1.0047 plus 0.045 times 5.1954. So we have that C sub P of the mix is equal to 1.1933 kilojoules per kilogram degree K. I can then substitute, so now it's adiabatic, so Q is 0. There's no work done. There's no paddle going into or out of the system. There's no work done. And so I have M dot A C sub P A T A plus M dot H E C sub P H E P H E is equal to M dot of the mix, C sub P of the mix, T mix. So I'm going to substitute all that stuff in, and we'll have the following. So I substitute in, and so we have 0.9397 times 1.0047 C sub P of the air times the temperature of the air, 313, plus 0.0436 times 5.1954 times 373 is equal to 0.98, the total mass flow rate, 9833, C sub P of the mix, 1.1933, and the temperature of the mix. So I have T, so then I have T mix, and if I solve for T mix, it's 324.8 degrees Kelvin, or 51.8 degrees C. So I had this coming in at 100 degrees C, this coming in at 40 degrees C, and the mixture leaves at 51.8 degrees C. And now what we're going to do is we're going to find the entropy production for all this. So this, like, oh my goodness. So what we're going to do is now we did this, so I know the total pressure here. So this is P total, right? And this is going to be equal to the sum of the PI. So whereas the helium came in at 103, this came in at 101.3, they leave here, so the partial pressure of the air makes up part of this, the partial pressure of the helium makes up the other part of the total. And remember that PI is equal to YI P total. So when we do all this, we'll be looking at finding the entropy production for this process, and we have that the entropy production is the change of the entropy for each one. Sometimes one will be negative, one will be positive. We'll find out what happens. So we have that the entropy production is equal to the sum of the del SI. So we're finding it out for I is equal to air, I is equal to helium. And so if I look at this equation, so S2 minus S1. So if I look at this is the entropy equation that we had in chapter 8. Now we're going to apply it to each gas. So this is equal to C sub P times the log of T2 over T1 minus R times the log of P2 over P1. And P2 of the air is equal to Y of the air times P total. So this is equal to 0.746 times 101.3 is equal to 75.8 kPa. So the partial pressure of this 101 for the air is 78, and so the partial pressure for the helium, P2 of the Ag, is obviously the difference between the two. And so if I find that, it's 25.5 kPa. So I can subtract this from 101.3, or I can use this Y sub Ag times P total to get the same result. So now I can apply this equation because now I know this term, right? So I know this term, and I know the temperature, all the gases this, I know the initial temperature, etc. So I can find out what this is for each of the gases. So I have m dot A times S2 minus S1A is equal to C sub P 1.0047 times the log of 324.8 over 313 minus R 0.287 times the log of 75.8 over 101.3. So I'll have that this m dot A times S2 minus S1 the air is equal to 0.1204 kilojoules per kilogram. Let me change that. Since I multiplied by the mass flow rate, it's 0.1131 kilowatts per degree K. Now, the deal here is that if I just had this per unit mass, then I can't add them together. So I have to have this on a time basis. Notice here, the units are kilowatts per degree K. And so if I do the same thing for the helium, it'll be kilowatts. I can add kilowatts and kilowatts together. And so if I do the same thing for the helium, and I'll multiply it by the mass flow rate of the helium, so we'll do that. So I have the mass flow rate of the helium times all this other stuff. And so I have C sub P 5.1954 times the log of 324.6 over 373 minus R 2.077 times the log of the partial pressure is 25.5 over 101.3. And here, I'll get this value equal to 0.0934 kilowatts per degree K. And so if I add those together, the entropy production is going to be equal to 0.2065 kilowatts per degree K. So this gives us the entropy production. So we find the entropy production for this. And now, so I'm not the only one doing problems like this. I want you to have the pleasure too. So for homework, do 11.11, 11.19, and 11.25.